Welcome to EDU World Space.
In this video, we're going to be talking about what is the electric field at various points along the x-axis for this configuration where we've got two spherical volumes, both of radius big R, and both have a positive charge Q spread uniformly throughout them. And we're interested in the net electric fields at various points. So we're going to have to keep a couple things in mind when approaching this problem. So the first thing is that each sphere is going to have its own electric field, right? And they're both going to be radiating outwards from each sphere because the charge is positive. And electric field being a vector, this means that it's going to add up at different points. So to actually evaluate the net electric field, we have to sum up the individual electric fields coming from the sphere 1 and the sphere 2 at whatever point we're talking about. The second thing we have to keep in mind is that since these spheres are spherical volumes, the electric field is going to look different inside versus outside. That's why we have these two expressions right here. So if we're going to be considering points which are inside the sphere, we're going to be using this expression. And if we're considering points outside the sphere, we're going to be using this expression. Let's just quickly go over where these expressions come from, just for some background. So I've done the derivation right here, and I'll just quickly walk you through it just for some background. So let's look at Gauss's law, which is being used to derive these expressions. So for points outside the spherical volume in black with same radius big R and total charge Q, we see that for the Gaussian surface here, the surface area of this Gaussian surface is just 4 pi small r squared. So this becomes the left-hand side of Gauss's law. And the right-hand side, the Q enclosed is replaced by just all of Q, because you can see that this Gaussian surface actually takes up or encloses all of the original charge. But for points inside, it's going to be slightly different, because you can see that this Gaussian surface in red, while the left-hand side of Gauss's law remains the same as you can see here, because it's still a surface sphere of surface area 4 pi small r squared. But it doesn't enclose all of the charge anymore. So it actually encloses only some of the charge. And to find that out, we use a ratio right here. So we multiply the total charge by the ratio of the volumes. So the volume of the smaller Gaussian sphere to the volume of the bigger original sphere. So that's right here as shown. And when you simplify these out, when you simplify the expressions, you get these expressions that we started with, which we're going to use to actually figure out electric fields. So let's first look at what is the electric field at x equals 0. So right here at the origin, and we can immediately see that the electric field coming from sphere 1 is just going to be 0, because the point that we're considering is the center of the sphere. So the distance from the center of the sphere is just 0. But from sphere 2, we can see that the point is outside sphere 2. So that takes us to this expression where the distance, the small r, is going to be the distance from the origin to the center of sphere 2, which is 2r. So we're going to substitute that right here. And for the direction from this from sphere 2, we can see that electric field will be radiating outwards. So it's going to be pointing towards the left, so the negative x-axis. So writing this out gives us something like this, where we add up the electric fields from E1 and E2, where E1 was just 0, and we substituted 2 times big R in this expression for E2, and we put a negative unit I vector to denote that the electric field is going towards the left-hand side. So this gives us electric field at x equals 0. Now let's look at electric field at x equals r over 2. So somewhere here, where you can see that the point is inside sphere 1. So we're going to be using this expression where you can substitute for small r big R over 2, because that's the distance from the center to the point that we're considering. And the direction is going to be towards the right, because electric field, as I said, is going to be radiating outwards from sphere 1. And from sphere 2, you can see that the point right here is outside sphere 2, and the distance between the center of sphere 2 and the point is 3 over 2 big R. So that's going to go right here in place of small r, and the direction again is going to be towards the left. So writing that out gives us this, where, like I said, we substitute big R over 2 in this expression for E1, and we substituted 3 times big R over 2 in this expression for E2, where the unit vector is going to be negative because the electric field is going towards the left, and simplifying the expression gives us this final expression for the electric field at x equals R over 2. Now let's look at what is the electric field right here at the edge of both our spheres. So at x equals big R, um, and we can see that we can use the E out expressions for both spheres because we can consider the point to be outside from both spheres, but we can immediately see that from the centers of both spheres, the distance to this point is big R. So the magnitude of the electric field is going to be the same coming from both our spheres, but the direction from sphere 1 is towards the right, and the direction from sphere 2 is towards the left as they're going out, radiating out from the spheres. So we can, by intuition, see that the electric fields are going to cancel out, and when we write it out, our suspicion is confirmed because we can see that when we substitute big R in our E out expression, we see that the magnitudes are both the same, but the unit vectors are opposite in signs because E1 is going towards the right and E2 is going towards the left. So this cancels out to give us 0. Finally, let's look at electric field at x equals 3 times big R. So that's the edge of sphere 2 right here. And we can see that this point can be considered to be outside from both spheres. So we're going to be using this expression in both cases. And from sphere 1, the distance from the center to this point is 3 times R. So that's going to go here in place of small r. And for sphere 2, the distance from the center of sphere 2 right here to this point is just big R. So again, that's just going to go here. And in both cases, the direction is going to be towards the right because in both cases the electric field is pointing outside from our spheres. So when we write that out, we get from E1 this expression right here where we substituted 3 times big R for the distance. And the direction is positive, so that's positive unit I vector. And for E2, the distance is just big R, so that's this distance. And the direction is again positive. And when we sum that up and simplify, we get this expression. So these 4 are the expressions. So that's the electric field evaluated at 4 different points along